Alright, in this video I'll be covering West Coast drivetrain gearboxes and how to make them, and this will be the first CAD challenge. So hopefully by now you've seen what a West Coast drivetrain looks like. Here I have the CAD of one pulled open, and basically so far we've been able to make the frame, all these 2x1s here, the gussets, and as well as the hex shafts that go in here. But now we'll get to the actual moving components, which is the gearbox. Now I'll just show you what the gearbox looks like, how it works, how it transfers power, and then we can actually get into making one. So as you can see here, we've got two motors, and we'll dive deeper into the gearbox itself. But as you can see, there's two motors here which power these gears, and the gears transfer power directly to this wheel. And then there's also these two loops of chain here that will transfer the power to these outer two wheels over here. And that's how the robot's able to move. These wheels are 6-inch wheels, and that's how it translates power. So if we open up a gearbox here, as you can see, we can take a closer look here. Two motors, there's a bunch of gears here, and this is the hex shaft that transfers power to the wheel. And you see these spiky things here, these are called sprockets, and these are the ones that connect with the chain and allow the other two wheels to move. So looking at a gearbox, let's dissect this gearbox here. So first of all, let's start with motors, right? What motors are these? How do you decide on motors, etc.? So in the FRC world, we have quite a few motors, and so we'll go through them one by one, right? So here is the motor you saw in the gearbox. This is one of the newest motors. It's called the Falcon 500, and this motor is extremely powerful and extremely efficient. So this is a motor that you would use on a drivetrain or other applications where you need a lot of power, such as the climber, for example, in the 2020 robot. And the next motor we have here is a Neo motor. It's made by a different manufacturer, but it's similar to the Falcon in that it has a lot of power and it's very efficient, and you'll also see it in drivetrains as well as other high power demanding applications. This next motor that we have here, this is an older motor that's been around for a while. It's called the Sim, and as you can see, compared to these other two motors that we just went over, the Falcon and the Neo, it's a lot bigger. And the reason for that is that it's an older motor and it's a brushed motor compared to these two, which are brushless. Now I won't get into the nitty-gritty details of what brushless and brushed means, but basically motors that have a brush in them, they have higher friction and they're less efficient. So for the amount of electrical power that we're giving them, they can't produce as much rotational power compared to these brushless motors here. And so that's the Sim. It is, although, a very robust motor. Like compared to these two other motors, this motor can take a lot of abuse. Gearboxes that aren't designed well, you can put in a lot of heat and temperature into these motors and they'll be able to survive. So it's a very, very robust motor. This next one here is called the Mini Sim, and it's very similar to the Sim in its construction and its size, except that it's a little bit shorter, and because of that it offers a little bit less power than the Sim. And so you'll see this commonly on medium power applications such as pivoting an intake or pivoting an arm, but there's a lot of crossovers between which motors you can use because they're fairly close in their specs to each other. The next motor that you will see used very commonly through FRC is the 775 Pro. So this motor, as you can see, is far smaller than these other motors here, but it is also a very efficient motor. It's not brushless, it is a brushed motor, but compared to the Mini Sim and even the Sim, it is very, very efficient. So this is why you see this motor commonly be used for intakes, for storage, for even elevators that don't need to climb. And you'll often see it paired with a versatile planetary gearbox so that you can get a reduction out of it. Basically, it'll give you more power, right? And the final motor we have here is actually a very new motor. It's called the Neo 550, and as you can see, in comparison to all these motors, it's very small. It is a brushless motor, and it offers similar power to the 775 Pro, a little bit less because of its smaller size, but this makes it perfect for an application like an intake where you don't need a lot of power, and having the need for a smaller amount of space makes it really good because you can fit this motor in far smaller spaces than the other motors over here. And I have this spreadsheet over here with details about each of these motors, as you can see here. So, and again, you can look here, the Falcon 500 has a lot of power. This does not determine like the most powerful motors ever. This is not one true stat for everything, but you can see it significantly has a significantly lot more power compared to the other motors over here. And here, if you look in the free speed column, you can see the speed that these motors have if there's nothing on them, right? So if I were to plug a Falcon 500 in, I would get about 6,000 revolutions per minute. If you were to plug a 775 Pro in, you would get about 18,000 revolutions per minute. And so these speeds here are what determine what our gearbox may look like, because obviously if we have an arm, for example, right, we don't want it to be flipping around back and forth at 18,000 RPM because that's way too fast and it's uncontrollable. Right, so again, if you go to the Falcon 500, for example, that we used on our drivetrain, so we saw it has 6,000 RPM, right? And we're using 6-inch wheels here. So if we wanted to calculate how fast our robot's going to move, we would just need to find how many revolutions this wheel, the RPM this wheel's moving at, and the circumference of the wheel. That way we can know how far the robot moved or how far back it moved, right? So if you do the math, 6,000 RPM or 100 revolutions per second with a 6-inch wheel, and the circumference of that would be 6 times pi, you get about 157 feet per second. And obviously that's not feasible. Our robots don't move 150 feet per second. So that's exactly why we need a gearbox, because we can't move at those high speeds. The second reason, and the more important reason for a gearbox, is these motors, when they're spinning at 6,000 RPM, they don't have a lot of power. They cannot push a 120-pound robot across the field. You can think of these motors without anything else on them, like over here, without the gearbox or anything. They're like sprinters, where if you leave them by themselves, they can go really, really fast. But the moment that they have to carry any sort of weight or any load on them, such as a whole robot, they can't go very fast at all, or barely even move. So what adding a gearbox does, it converts it from like a sprinter to a bodybuilder, because what gear ratios do is they reduce the speed of the motor. So our output shaft over here, our wheels are not going to be spinning at 6,000 RPM. So the bodybuilder isn't going to be running as fast as our sprinter, but when there's a 120-pound robot on top of it, it's still able to run at a similar speed without slowing down because it has a lot of power. So that's the whole point of having these gearboxes. And so let's get into how gears work, right? So I'll pull out some of the components here so it's easier to see. And if you look here, let's move these out of the way. Right, so if you look here, our motors are connected to these small gears over here, right? So the motor, if you look over here, all these motors have shafts coming out of them, and you can slide gears onto them. So what happens here is we have this gear here which is attached to our motor. So this gear is spinning at 6,000 RPM. And this gear is connected to this far larger gear over here. And this is the key to using gears. Basically, anytime you have an input on a smaller gear and you have it connected to a bigger gear, what you do is you reduce the speed, so it goes from 6,000 RPM to maybe 3,000 RPM or 2,000 RPM. But you increase the amount of power it has. So maybe this motor alone could, push like 5 pounds of weight, but now with the reduction here, anything that's connected to this gear will be able to push 30 pounds of weight. And what we do on a drivetrain gearbox is we have two sets of gears. So first we have our motor with a small gear connected to this large gear over here. And then we have a second set of gears over here. So if you look, there's a hex shaft that goes down the middle over here. So this hex shaft is what's connecting these two gears together. So both of these gears are going to be spinning at the same exact speed, which is going to be less than the 6,000 RPM over here. And what happens is this gear over here is small compared to this other gear. And we have a second reduction here. So we go from 6,000 RPM to a slower speed, more power. And then we go from this slower speed, more power to even slower speed and even more power. So now instead of being able to push 30 pounds, we can actually push a 120 pound robot. And we're going even slower. And then obviously on this hex shaft, we have our wheel, which attaches right here. As you can see, there's the hex shaft, there's the wheel, and you have the two sprockets, which will join in with the chain and drive the other wheels. So that's the basic setup of a gearbox. And now I'd like to introduce you to the JVN calculator. So the spreadsheet here, if you go to custom 1-speed drive, we'll have a link to the spreadsheet, and what you can do is go on file, make a copy, so you can keep your own personal version of this spreadsheet. And this spreadsheet basically allows you to design and calculate a lot of the variables that are required when you're making a drivetrain and making drivetrain gearbox. There's other uses for this spreadsheet as well. But as you can see, this spreadsheet here, there's a lot of things, so we'll go through it slowly. The first thing here is your motor. So what motor are you going to be using to drive your gearbox? Now, in the gearbox over here, we're using these Falcons. There are other teams that use different motors. So, for example, our team in 2019, we used the Neos because the Falcons weren't around then. And before that, we used the Sim motors. Other teams have different ideas and they use different motors. So we'll select the Falcon 500 from this list of motors over here. And as you can see, the stats over here for that motor automatically update, so you don't have to worry about changing them. And then we have the number of gearboxes in drivetrain. So what this means is, in your full drivetrain over here, how many of these gearboxes are you going to have? So you could, in theory, have one gearbox and then have chain here and then maybe a long hex shaft that connects the other side, and so you'll only need one gearbox. But obviously if you have one gearbox, you're going to need a lot of power from it because you need to push the whole robot using only this one gearbox. So what we usually do in West Coast drivetrains is we split it into two gearboxes, one on each side, so that they each have to take only half the load. It also makes turning easier because we can control each side individually. So we're going to have two gearboxes in our drivetrain. And then this next box over here is the number of motors we have in each gearbox. So most commonly you'll see two motors in a West Coast drivetrain gearbox because two motors have enough power. There are some gearboxes, some teams that make gearboxes with three motors in them. And the purpose of the third motor here could be that if they're using Sims, because Sims have a lower amount of power compared to the Neos or Falcon 500s, they need more of them. And it can also help with managing the load on each motor, because if you only have two motors, those two motors have to share the load of moving the robot. But if you have three, you have more motors to share the load, and so each motor has to take care of less, which makes it can make it easier for the motors to survive, and it lowers the chances of it heating up too much and causing other trouble. But it does take up more space. So that's what the number of motors per gearbox is. So here we'll go with 2. And then here we have the total weight that these motors are going to be pushing. So in the rules, in the game manual, you'll see the robot weight limit is 125 pounds. But that 125 pounds excludes the weight of the battery, the bumpers. And so what we want to do here is, instead of that 125 pounds, we want to enter 154 pounds, because when you add the battery and bumpers, that's about where the weight ends up being. And obviously this is like the worst case weight, so if we go full 125 pound robot plus battery plus bumpers, this is where it would be. And it's a good idea to design with this weight in mind, unless you know for sure your robot's going to be lighter, so that you can make sure that even if your robot goes really heavy, you can still have a driving robot. Because I can design for a 100-pound robot, but if my robot's overweight, this gearbox will be underpowered and I won't be able to do much with it. So I'm going to have 154 here, and this weight on driven wheels basically means that the wheels that are going to drive the robot, how much of the robot's weight is on them, and it's 100%. All of the robot's weight is resting on these wheels over here. And so then we get to wheel diameter in inches. So here in this case we're using 6-inch wheels. Commonly drivetrains use anywhere between 4 to 6-inch wheels. Generally, the smaller diameter of a wheel you have, the smaller gears you can get away with. And the bigger diameter you have, you need a bigger gearbox for it. But it also means with smaller wheels, you have smaller ground clearance. So if there's a big bump in the field, for example, it's harder to cross it with a 4-inch wheel in your drivetrain versus 6-inch wheels. There are also bigger wheels. So if we look in the parts library under the wheel section, you can see there are these 8-inch wheels. And in a game like 2016, where there were obstacles on the field that you had to cross, those big wheels can come in handy for allowing you to have enough clearance between the bottom of the ground and your robot to, cross obstacles. So that's wheel diameter. Wheel coefficient, you don't have to worry about this number too much. It is basically the coefficient of friction between the wheels and the ground. It's basically, this number is generally between 0 and 1, and anything near 0 is like an ice skating rink, and ice skates on an ice skating rink, there's barely any friction, that you can slide very easily, and anything near a 1 tends to be a lot of friction. So a rubber tire on an asphalt road, or in this case in FRC, are rubber tires on carpet. So we don't have to change that number generally. And then we get to this section over here where you can enter your gears. So the driving gear is the input. So this is where your motor is being powered, right? So this first set over here is whatever the gear on your motor is, right here. And so if we again look at the parts library, if you go under motion, gears, and we'll look at these motor gears over here. So for Falcon, there are separate gears. We can just look at these here. And as you can see, there are all types of gears. So there's 8T, which means they have 8 teeth on them. There's 9 teeth, 10, 11, 12, and 13, 14. Those are the sizes available on the motor. So in this place over here, we can have anything from 8 to 14 teeth gears. And basically, remember when we talked about a small to a big gear, the small and the big comes from the number of teeth any gear has. So a 9-tooth gear compared to this 46-tooth gear, there's a ratio there, the 9 to the 46, and that determines how much do you trade off your speed versus how much power you trade off. So a 10-tooth gear with a 50 combined with a 50-tooth gear is a 10 to 50 ratio, or 1 to 5. So if I have my 10-tooth gear on my motor and my 50-tooth gear on my wheel will be spinning 5 times slower than my motor because of that 1 to 5 ratio, but it will also have 5 times the power. So that's how gear ratios work. And what we want to enter here is the size of our gears. So in this case, we have a 9-tooth gear. So this will be 9. This could be 8, this could be 8 or 10 or 14, etc., etc. So we'll have 9 teeth here. And then this driven gear is the gear that's connected to our driving gear. So in this case, the gear that is connected is the middle one over here, which happens to be 46 teeth. So what we'll do here is we'll make the driven gear 46. And so when you're designing a gearbox by yourself, this is where you can experiment around with different gears to see what speeds you're getting, as well as how much power you're going to get. So we have a second driving gear over here, which would be the small gear, right? So anytime you have any two gears, the gear that's going to be the input is the one that's being provided the power from your motor, and the driven gear is where your output's going. So the wheel, an intake, etc., right? So here we have a 20-tooth and a 44-tooth gear. So 20 and then 44. And as you can see, whenever you change these numbers, the numbers over here update. And what we have here is the drivetrain free speed. So if my drivetrain was held up in the air and the wheels weren't pushing anything, this is how fast my robot would be moving. or the wheels would be moving about at this speed, which is 14.8 feet per second. And when you're looking at drivetrain speeds, generally aiming for anything in the realm of 13 to 15 feet per second is a really good speed, because it's not super fast, but it's also not really slow. Now, the speed that you should be aiming for depends on the game, right? So a game like 2017 required you to sprint from one side of the field to the other side and come back. And in that kind of a game, you want to have a high top speed. So you would aim for something like maybe 15 or 16 feet per second. But in other games, you don't have to make long sprints. They're short runs, and so you can go with the lower drivetrain free speed. And again, remember that idea where the speed from the motor is traded for power. So the slower this drivetrain free speed is, generally speaking, you're going to have more power. So if I make these gears huge over here, I'm going to be going 1 foot per second slower, but I'm also going to have a lot more power. And why do you need power? Well, if you have a really heavy robot, you need power to move that robot. And in a match, whenever you have a defense robot, another robot that's blocking you, that's when you need this power, because if your motors are not able to cope with another defense robot, your robot's going to be stuck, and you have to find a way to juke the other robot, and you can't simply just push through them. And so it's important to consider where defense would be and how big of a threat is defense to your robot. And that can drive the decision to make sure that this speed is good enough and you have enough power. Now, this adjusted speed over here is basically what would the speed look like in real life, because obviously this calculation here doesn't take into account friction or the random sort of forces that can happen in a real life environment. So this adjusted speed here sort of shows you what this might look like in real life. But again, this number it's hard to predict what this number would be, and again, it changes based on conditions, so we generally don't rely on this number a lot. The free speed number is what we go off of and what we use to make our decisions. And then we have this pushing current draw per motor. So basically, the way motors work is our battery supplies them with electricity, and you can think of electricity as food for these motors. And so whenever the motor is just running freely, it doesn't need a lot of energy, so it doesn't ask for a lot of electricity. And when we say current in electricity, it's like the amount of electricity, so it's the amount of food that my motors are asking for. And when there's not a lot of load on them, they don't need a lot of food because there's nothing much to do. But when a robot is stuck against another robot, for example, right, and we're trying to just push that other robot away so that we can get on with our game, that's when the motors are putting in their highest amount of energy, because they're trying to push against another robot. It's like a huge heavy box they're trying to push against, and that's when they want the most amount of food or the most amount of energy, so the most amount of current. And basically this number here is how much current would my motors want when they're going full power, when they have to push against another robot. And that's what the 65.89 amps is. Now, this number, basically this is what you use to make sure that you have enough power, right? Because the free speed doesn't tell you how much power you have, it tells you how fast you're going. This number here will give you an idea of how much power do you have. So if you look here, if I were to not have a big gear ratio, right? If I were to change these numbers, make them smaller, as you can see, my current here increases because my gearbox isn't trading a lot of speed for a lot of power. So what happens is my motors need more energy whenever they're having to push against another robot. Whereas if I go in here and I change these numbers to be far bigger, as you can see, this number here goes down quite a bit, and that means my gearbox converts so much of the motor speed to power that the motors themselves don't need as much energy. So you can think of the gearbox as basically adding muscle to the motor, and if you have a really big gearbox with very big gears, you're adding a lot of muscle, so the motor itself doesn't have to do a lot of the work. But when you don't have a good gearbox and it's not good enough, what you end up with is the motor having to do a lot of the work, and so it needs a lot of energy. Alright, so going back to our gearbox over here, again we have 9 teeth on the motor, as you can see here, connected to a 46 teeth gear over here, and then the next stage is a 20 tooth gear connected to a 44 tooth gear, 20 to 44. And then these other boxes over here, the ones with the ones, are left at 1 because this allows you, in case you have more stages, so in case you wanted to add another set of gears over here, we could do that, and you can fill these in with other gear sizes if we were adding more gears. But because we're only adding 2 sets of gears, we're going to leave these at 1. So as you can see, we end up with a free speed 14.85. You want to aim around 13 to 15 feet per second, so that's where we're here. Now with the current draw, as you can see, we're at around 66, 67 amps. Really what you want to try to make sure is that your current draw isn't really exceeding a number like 70 amps. And this number here, now you might remember that on the robot, the PDP, the electrical component gives power to the motor, it has a limit of 40 amps. So it doesn't make sense that the motors can ask for 66 amps and still work. And the reason for that is that 40 amp limit is not a hard 40 amp limit, it's a soft limit. So basically, if my motors were asking for 66 amps for 10 minutes straight, that PDP component wouldn't allow my motor to have that much energy. It won't allow it to have that much food because it will starve the other parts of the robot. But if my motors ask for 66 amps for a fraction of a second, it will actually allow it to have that much energy. So this is why the 66 amps is not a big deal, even though technically we should not exceed 40 amps for the most part of driving the robot. Now this final category over here, wheel slipping at stall torque, what this means is basically our motor and the set of gears and the shaft and the wheel that attaches to it provide a certain amount of rotational power. Rotational power is also known as torque, and basically my gearbox asks the wheel to put down, let's say, 10 pounds of force, right? The problem here is just because my gearbox is making 10 pounds of rotational force doesn't mean that my wheel can put down 10 pounds of rotational force. How much force my wheels can put down depends on how much friction they have between the carpet and the wheel, as well as the weight of the whole robot. You can think of this as when you go ice skating, and if you just try to move your feet and go forwards, you're not able to go anywhere, because even though your muscles are capable of providing enough force to move you forwards, there's not enough friction between the skates and the ice to allow you to go forwards. And you have to, turn your feet and use the edge and sort of dig into the ice to move forwards, because that way you can put in that much force. Basically what this means here is, if my motors are pushing against another robot and we're going full force and we're asking for 67 amps of energy, are my wheels going to be able to deliver that much torque? And what slipping means, my wheels won't be able to deliver that much power. And what will happen instead is my robot will go up against another robot and try to ram it, but these wheels will be just spinning freely in place, and they won't actually be stopped and trying to push against the robot. Now at first you might think then that's useless, because you want your robot to be able to push against another robot, right? But actually having your wheels able to slip isn't a bad thing. And that's because, remember, our motors are asking for energy anytime they have a load on them. So when a robot's against another robot and they're asking for energy, right? Remember, 66 amps isn't actually allowed for a long amount of time. And so if this was a no, what that would mean is, for the whole time that a robot is next to another robot and trying to push it away, these motors are constantly asking for 66 amps of energy, and that will starve the rest of the robot. And there's a condition called brownout, which basically means the central computer of the robot doesn't have enough electricity to operate with, because maybe other motors are taking too much of that electricity, and you end up with losing communications, your robot isn't performing as fast as it should, and it leads to a whole set of other problems. It also means that your motor is going to get really hot, and whenever motors get up to a really high temperature, they stop operating as well. So that's why if your wheels are able to slip, basically it means my robot and my drivetrain is going to drive really well until it hits a wall or hits another robot, and after a certain point it's going to say, okay, I can't provide this much power, my wheels can't provide this much power, I'm going to stop and I'll just let my wheels slip. I'll just run in place so that I don't kill my motors. And this way you make sure that you have enough power, you have enough speed, but you also won't kill your motors in the case that you have to be against defense for a long amount of time. So this is how you use the JVN calculator's 1-speed drive option. Now the 1-speed basically means that these gears here don't change, and anytime I plug in my motor, I'll have the same exact speed coming out. You can also have 2-speed gearboxes, which basically what they do is they have a second set of gears that you can switch to. So you'll have a setting for, let's say, defense. In your defense setting, your motors provide a lot of power. It's all muscle power. And then you have a high speed setting where you don't have as much power, but you can sprint across the field. And that can be useful for games where you have long sprints and a lot of defense, because then you can switch between a really defense focused gearbox and a sprint focused gearbox. So that's how drivetrain gearboxes are. And in the next video, I'll be covering how to make basically this first part of the gearbox, this plate itself. Thanks for watching.